Good afternoon, everyone. Good afternoon. First of all, thank you. Thank you so much for taking the time to come here and learn about our systems and silicon infrastructure innovations. This is really the foundation or the bedrock of Azure. And just a show of hands, people get to watch Satya's keynote this morning? OK, good. Many of you did. But if you didn't, no worries. We'll be covering all the announcements and much more. And we'll be leaving some time for Q&A as well. I've got some cool pieces of hardware with me as well. So if you want to go to the show floor or come back here and take a look at it, that would be great. Before I get going, a quick introduction. So I'm Saurabh Dighe, and I am a part of the Hardware Systems and Infrastructure organization. I'm responsible for planning as well as the architecture. I have with me a colleague of mine who's the Vice President of Cloud Hardware Engineering. And so between the two of us, we will be tag teaming this presentation, and we'll be answering questions at the end of the day as well. So before I dive into the tech and the announcements, I really wanted to spend a few minutes on just kind of talking about our vision, our approach of cloud and AI infrastructure, and also talk about the changing landscape that we're all going through today. So at Microsoft, we think of Azure as building the world's computer. And we are running right now in 60+ regions, 300+ data centers all across the world. And just to visualize, a region could have numerous data centers. And I'll pick an example, Dublin. Dublin is a region which has numerous data centers and is aggregate about 2 million square feet of data center space in Dublin. So if you want to conceptualize, visualize that, that would be close to about 35 American football fields. So that gives you a little perspective of scale. And so 60+ regions around the world. And then you're trying to connect all these regions with high-speed fiber. That's about 275,000 miles of fiber, about 190 points of presence in metro locations. And so whenever we are building infrastructure, scale is always top of mind for us. And we're always growing and building this infrastructure. But the world is changing. And it's changing in 3 fundamental ways. I think we all know that the demand for AI infrastructure is skyrocketing. The fact that you need more energy-efficient systems and sustainable energy is actually now more than ever. And with AI and the current security and threat landscape, trust and security are top of customers' minds. And I'm going to capture kind of these 3 trends in 3 charts. The first one is what we call the scaling laws of AI. And what essentially this is, and this is an empirical one, right? This is based on observation, just like Moore's law was based on observation. And what it says is that, hey, the AI performance and system capability is almost doubling every 6 months compared to what we've seen with Moore's law, which was every 2 years. So you can definitely see the acceleration in the capability in the last few years. What this also means is that traditionally, CapEx was really driven by, like, say, for example, the oil and gas industry or the retail industry, right? But that mantle has now shifted to technology. Like a recent report from Morgan Stanley basically said that, hey, the large 4 hyperscalers are going to probably spend more than $250 billion in CapEx in 2025. And what this means is that we are in the midst of the most ambitious and complex infrastructure build-out of our generation. And it's really infrastructure innovation that's going to help unlock the next technology frontier and not the other way around. Okay? So chart number 2 is with all that infrastructure demand, there's a growing demand for global electricity everywhere. And the International Energy Agency has kind of put out a report that says between 2022 and 2026, we could have a growth about 1.4 to 2x in data center energy demand. That could be the equivalent of adding a Sweden or a Germany to the global consumption. So pretty large. And then chart number 3 is around security. And according to the World Economic Forum, if cybercrime was a world economy, it would have been number 3 in the world, right behind US and China, which is astounding. That's going to cost us $8 trillion in 2024. So as the world is changing, so is our approach to building the world's computer. And so if there's one takeaway from this session today, it's actually that for cloud and AI infrastructure, really scaling performance while keeping capital efficiency, energy efficiency, sustainability, and security requires every engineer to reimagine the paradigm. These traditional boundaries between silicon and servers and racks and network and data center, they all have to blur. What really matters is when the software, the hardware, the data center, the facility, they're all co-designed, co-optimized as one system. And so this has been our guiding principle for the last several years. And we're going to talk about these 3 things today. But underlying all these 3 things, we're going to talk about Microsoft custom silicon innovations. We're going to talk about how we are bringing the best of the industry and the best of Microsoft to bring choice and flexibility to our customers. And we're going to talk about systems and infrastructure innovations that really power Azure. But underlying all of this is that theme of really driving end-to-end system optimizations. So let's talk about our custom silicon portfolio. And yes, it's growing, right? We have now announced Cobalt 100, which is our compute offering, Maia 100, which is the AI accelerator, and Azure Boost technology. And they're all running in our fleet. They're live. They're serving production workloads to many of our customers. And so I'll talk about a little bit of our forward momentum in these products. But then the exciting 2 new announcements, 2 new members of the family. We're announcing our first in-house data processing unit of the Boost DPU that's really architected to accelerate data-centric workloads, and I'll talk a little bit about that. And then we're also announcing our first integrated Azure hardware security module that's built for key management and enhanced protection, as well as meets the most stringent standards in security. So we'll do a little deep dive on both. But starting with Azure Cobalt, so Cobalt 100 is really our first ARM 64-bit Neoverse architecture. It was really built for delivering the best performance per watt. And it is our most efficient compute offering in the fleet today. Also, what's important is that we have made sure that Cobalt 100 seamlessly integrates with the broader Microsoft infrastructure like networking and storage. So what customers get is really the high performance of Cobalt 100 at the system level, but also the energy efficiency that's so critical as we scale our compute fleet, and it's so critical for any hyperscaler. And we've got great testimonials now from our customers like Databricks, Siemens, and Snowflake. We're actually already seeing about 50% performance per dollar improvement on Azure Cobalt over their previous generation VMs. And to dig a little deeper, the big news here is Azure Cobalt is now generally available, right? So it's really available across 14 regions We are continuing to deploy it in more regions every day. We've also made multiple VM families available, so you can choose the right VM family, which is really the memory to vCPU ratio that is required for your workloads. For example, if your workloads don't need a lot of RAM versus compute performance, you could use the 2:1 ratio. That's great for microservices, small databases. If you want to upgrade to a 4:1 ratio, that's great for application servers, web servers, cloud-native services like AKS. And then if you move to a higher memory to ratio, like an 8:1, you could do in-memory caching, database analytics, and large databases. So we really provide you that flexibility and choice along with storage offerings, again, available across all the regions, 14 regions today, and continuing to grow. The next product I'm going to talk about is Azure Maia. Maia is a specialized AI accelerator, again, designed to accelerate inferencing workloads in the Azure AI fleet. And it really has a few features, like it has got a high-speed tensor unit. It really supports multiple data formats that are prevalent in the industry today. It has an integrated backend Ethernet so that you can now communicate between many of Maias together with a high bandwidth, low latency. And what it makes sure is that it is really running Azure OpenAI services now in the cloud with, like, for example, in the US East region. And Satya kind of showed in his keynote a demo where we're really, like, one of the use cases of AI is being able to streamline customer support experience. And we are demonstrating that now with Maia 100 running on Azure OpenAI services, and it will be brought to the support community through Microsoft M365, the initiative under M365. Now, Maia 100 was not designed just to be silicon, right? It was designed as an entire system. And what I mean by that is it was designed to be liquid-cooled. We have a liquid heat exchanger rack that goes and is deployed with every Maia so that we are not constrained to just doing it in a native liquid-cooled facility, but we can do it globally everywhere. We also made sure that there were about 4 Maia chips in every server, and there are 8 servers in every rack. So we have a high density of these in every rack that is integrated with power and networking. And what we have done is we have taken built a complete SDK so that our developers can take a model that's built in PyTorch, a model that could be built in Triton, and seamlessly move it to the Maia system. And the main message here is that it's really this ability to take the models, co-design the silicon and the system that unlocks energy efficiency and the best economics for token generation in the future for our fleet. Moving on to Azure Boost. Azure Boost was announced a little earlier. And what this is it's a purpose-built hardware, really able to then offload server virtualization processes that were traditionally they were running on the hypervisor or the host OS. But now we have offloaded all those processes into this special purpose-built hardware and software. And that improves performance, it improves reliability, it improves security. For example, we're able to now isolate the control and data plane from the customer-facing resources. And Azure Boost is now shipping with every Azure server in our fleet. It's currently running millions of customers' VMs and able to deliver that network performance. In fact, we are announcing more upgrades and performance boosting technologies. Like, for example, our local storage is now able to achieve about 36 gigabytes per second, which is 2x of more of what we had announced before. We've also been able to move our IOPS to about 6.6 million IO operations per second on local storage. On remote storage, we're able to achieve about 17 gigabytes per second and about 750,000 I/O operations per second. And so this rounds up our first three silicon, which is the Cobalt, the Maia, the Boost. These are products that are in our fleet today, running production workloads, serving many, many customers. And what's exciting is these are multi-generational products. We're already working on the next few generations of these products, and we'll continue to deploy this in our fleet and continue to create higher performance and energy efficiency for our fleet. I'm going to shift gears a little bit and talk about the data processing unit, or the DPU. We're definitely in the AI-centric era, but we're also in the data-centric era. And there's vast amount of data that's really being transferred over the network today. And we saw a few years ago emergence of a completely new architecture. And people have asked us, why do you need a new architecture? And so CPUs, they're highly versatile, quite programmable. They do a great job of running through a set of instructions, sequential instructions. But when it comes to doing a lot of parallel math computations and vector math, we realized that, hey, GPUs were better, more efficient from a performance per watt perspective to do highly parallel tasks like pixel processing and now AI neural architectures. Similarly, there's an emergence of this new silicon really that's oriented towards high throughput data management workloads that have a lot of context switching and granularity. And let me help you conceptualize this from a programming standpoint. What really is you think of this as workloads, right? The work comes in packets. It packets over the network or our PCIe interface, for example. And this architecture, what it does is it takes that data that comes in these packets and takes it through a series of transformations and operations. But the instructions are not too long. There's a short run of instructions. But you have to retain a lot of state. You have to retain a lot of different flows that come through on the network. You have to be able to context switch really fast. And we've realized that a specific processing architecture, a data flow architecture, is much, much better suited. That really sits at that interface of the network and the host endpoint. So today we announced our first in-house data processing unit, the Boost DPU. Like I said, it's really architected for Azure data-centric workloads. And it accelerates those workloads, and I'll give you an example of that. It's built in what we in a hyperscaling environment absolutely need, the reliability and the security. And we are actually testing our storage workloads on this architecture today, and we are seeing about 4x the performance and 3x lower power. That's a significant improvement to our storage fleet. And let me explain and let me unpack that a little bit for all of you. So what you see here now is on the left, I'll call it a traditional storage server. And what it is, it's got a compute subsystem. It's got an accelerator card that accelerates some data management functions, encryption, decryption, things like that. It, of course, has a PCI switch so that you can connect a lot of banks of media to this. And then it also has a network interface card that lets you talk to the outside world. What we have done is we have been able to integrate all of this functionality into one piece of silicon. And that silicon itself has been optimized for a data flow architecture. So you bring all this functionality together, but it's not just the silicon. Like I said, it's a system story. And we also have now a fully programmable data flow lightweight operating system running on top of this silicon. And the application layer, in our case, it's the storage stack, is also optimized on top of this operating system and the silicon. And so as you look at this vertical integration, this is what really delivers you 4x that performance of what you would got in a traditional server, and then 3x lower power. So very excited to bring this into our fleet in the very near future. The other announcement we did was around a special in-house security chip, the Azure Integrated HSM. But before I actually get into the details of the chip, I wanted to talk about the hardware security and systems architecture. Because we all know that security is not a single layer of defense. There's actually multiple layers and multiple technologies that have to be deployed across every surface that could be attacked. And so what this is showing is that we in Azure, for now many years, have been working on 5 key hardware technologies that all come together. And we know as security community that the promise and construct of software, when it's backed by secure hardware, that's really the formula for having the best security architecture. And so these 5 technologies, I'll kind of talk about it. The first one is confidential compute. This is really where we were working with our x86 CPU vendors to bring in specialized instructions for confidential computing that created a trusted execution environment and protected the data, the customer data on the VM, and kept it under a trusted boundary. We also worked with the industry to start Calyptra. Calyptra is an open source root of trust IP that the vendors, CPU vendors or other vendors who are providing components into this server and have firmware associated with it, they can embed Calyptra IP into this component, and it authenticates and attests all the firmware. So you can guarantee that firmware coming in is secure. We also have worked on a small daughter card. It's called the Datacenter Secure Control Module, DCSCM. And the DCSCM protects and secures the board management controller, because that could be an attack vector. And it's also a platform root of trust, so any firmware that's on the platform gets protected. I've talked about Azure Boost as our front end and a front end network, and that isolates the control plane and the data plane, so that provides an additional level of security. And then finally, the Azure Integrated HSM that we talked today kind of rounds this up as well. And let me talk a little bit about hardware security modules, because today, hyperscalers use hardware security modules, but they are centralized HSMs. What that means is these are big, bulky, heavy servers, and you deploy a few of them geographically distributed. And whenever an HSM service or a key management service is running on a server somewhere and has to do some key management operations, it has to traverse the network, go towards this centralized HSM, get the keys from it, or every time you operate in it and get the answers back. And that's not a scalable solution. It adds a latency and performance bottlenecks as cryptographic operations and key management operations start getting more and more prevalent in our fleet. And so this is really what we're announcing now, is the ability to take this HSM functionality and integrate it into every server that we ship in Azure. And it really isolates the cryptographic keys, keeps it within a trusted HSM boundary, delivers the enhanced security, but also the performance. It is designed to meet the highest levels of government standards, which is the FIPS 140 level 3. And like I said, it will be embedded in every server next year. And let me talk about it from a service point of view. Now, if you're running an HSM service And if you're looking at it and saying, hey, that's great, what I can do now is you have the confidential compute VM running on your host CPU. You can talk to an HSM service, which may get the keys from a centralized HSM for the first time, but the keys never leave the trusted HSM boundary because they're only released to this local HSM in your server. And then you can do all the key management operations locally, still within the trusted HSM boundary, without even the guest OS or the host OS seeing the keys at all. So it keeps us out of the equation as well. And it stays within that trusted HSM boundary, delivers that enhanced security, but also delivers additional performance because we have taken key cryptographic accelerators and put them into this HSM boundary. We have made this extremely secure, which means that even the interface between the host CPU and the integrated HSM is TDISP compliant. And we are also logically and physically, like intrusion detection and tamper detection proof. So that really ensures that we are meeting those high levels of standards that the NIST, the National Institute of Security and Technologies, has kept, the FIPS 140 level 3. So Azure Integrated HSM is obviously another step in our security journey. We are continuing to innovate across the security spectrum. And so in the last couple of months, we've made some additional announcements that I want to briefly touch on. I talked about Calyptra, but we also have now Calyptra 2.0 that is released open source. And this not only detects, but also protects and helps you recover from any malware or firmware that doesn't need to be in your fleet. We've also released Adams Bridge. Now, Adams Bridge is our first quantum resilient cryptographic accelerator. That's a part of Calyptra 2.0. And let me explain you why we believe this is a very critical and important step. We are seeing the rapid advances in the field of science with AI and also in the field of quantum computing. And the government has started to realize that quantum resiliency is a key initiative. And they've also started to publish standards for what quantum resiliency should look like. And in the era of quantum computing, one field that can be compromised is the traditional cryptographic algorithms. So we believe that quantum resilience and cryptographic accelerators that are quantum resilient are going to be extremely important for the industry going forward. And we're proud to be one of the first to open source this accelerator. The third announcement we talked about was what we call OCP. We did this with members of the OCP. It's safe. It's really when vendors and component providers are providing firmware to hyperscalers, they need a consistent way and a framework to audit the firmware. And we have a trusted ledger now through the OCP Safe framework. And between OCP Safe and Calyptra, we are providing the transparency and the assurance that all of the firmware coming in to the fleet will be secure, authenticated, and attested. So this kind of rounds up some of the security innovations that we are doing in the fleet. OK, so we talked a lot about Microsoft Cloud Silicon. And I'm sure if you have questions, I'll come back and answer them. But I'm going to hand it off to my colleague here, Gohar. And so Gohar is going to talk about our industry partnerships as well as systems and infrastructure innovations. So here you go, Gohar.
Thank you, Saurabh.
Thank you.
So you all heard a lot about what we are doing as innovation in the silicon space at Microsoft. But we're also partnering with our external partners. We continue to work with AMD, Intel, and NVIDIA because we want to make sure that our customers have the flexibility and the choice to fit what's best for their workloads over there. We are actively working on the roadmaps with these partners to make sure that we can influence what our customers need and actually make sure that we work closely to go give the solutions which actually is the right thing for Azure. We are introducing announcing two basically solutions today. One is NVIDIA. Everyone knows about the Blackwell platform. We are currently bringing up these machines, co-validating them with NVIDIA right now, along with some of our key AI leaders. The platform we are building over here connects the NVLink rack-level solution from NVIDIA with IB network, and it will connect thousands of Blackwell GPUs to basically give unparalleled AI supercomputing performance. The other thing which we are introducing today, and Satya talked about it, is the HBV5 VM. This is based on 5th generation AMD EPYC processor, only available on Azure. It gives about 8x faster performance than any of the competitors, and it's about 35x more performance than the end-of-life on-prem deployments which we have currently. It makes you available about 400 gig of memory at 7 terabits per second of speed. So these are solutions which we have worked very closely with AMD, and we are going to be bringing that to Azure. Now, one thing which you have been talking about, we have been talking about is silicon, be it at the security level, be it at the compute level, be it in the network level. But infrastructure is more than that. When you think about infrastructure, it is your silicon, it is your racks, it's your power delivery, it's your liquid cooling, it's your data center. Everything has to be optimized for the full stack to give you the right solution at the end of the day. So we're going to talk about some of the innovations in that space. But first, I want to go and explain what is happening with this infrastructure. If you think about it, what does a supercompute need? It requires a lot of compute connected together on low latency fabric, high reliability, so that you have it when it needs, it doesn't go down. That's very critical for this infrastructure. There's another concept which you will see over there, and you see the pod design. What is pod? Think of it as a lot of the accelerators working together and it's basically, to a workload, they act as one GPU or one compute unit. That is what. But when you have to go and pack all these together, that's basically we call a pod over here. So as you look at it, the number of these accelerators are increasing as we go and look at the next generation AI racks. What is the implication? You have to go and have a highly reliable cooling solution. We are going to liquid, right? We are basically going to cold plate cooling as we go to that, which requires heat exchangers. Now, think about it. IT rack, a lot of accelerators. How do I go cool it? Do I have to go build new data centers? Yes, you have to. But at the same time, the pace at which we have to move, we also have to be able to deploy them in our existing data centers. We have to make sure that we are able to go and take the maximum usage of the power which we have and deploy them there. The second thing is, think about it. If all of that rack, which is limited space, is going to be taken up by the accelerators, you also have to start disaggregating the design. Your power has to move outside from the rack. You might have to think about other solutions from that perspective. So the next two innovations from Microsoft, which we have, and I couldn't bring one of them over here, you will see why, is our heat exchanger unit. You saw one with Maia. This is the next generation heat exchanger unit. It's designed for high performance, for flexibility that it can deploy in any of our existing data centers, even if it's not liquid cooled. It's designed for high resiliency just because of the, you cannot go and have an IT rack go down because a heat exchanger or a liquid cooling or something has to be repaired in there. So it's designed so that you can hot swap a lot of the things which are needed in there without taking your workload down over there. You can go to Microsoft booth It's available to be seen over there. Please, if you want to go and, I have gone there and changed at least the fans myself, so you can go play with it. The second one is we talked about the disaggregation. We are moving away to the point where your power is going to be inside the rack. It has to be a disaggregated unit over there. We're designing the next generation power infrastructure. We are collaborating with Meta over there. It's a 400-volt DC disaggregated power unit. It scales from 100 kilowatts to about 1 megawatt of power. And it's going to be used not just on one solution, but it can be used across the Microsoft Maia next generation. It can be used with the NVIDIA solution. It can be used with any of the racks which we have over there. We continue to look at power and how do we go and efficiently, while we are solving for it for the next generation racks, we're also looking at it, how do we go and take the opportunity or the full power which we have in our data centers over there. Think of it this way. When you're basically designing a data center or provisioning the power, you do it for the worst case scenario. You know there is going to be maintenance windows. You know there is going to be times when you have certain data centers which are down. That is what I call as the provision power which is available to us. We also have to go and basically design that for the worst case workloads at the time we are designing the hardware. But these workloads change over time. We know basically that there is always a gap over there. Now, we are looking for how do we look at efficiency across the full stack. We're looking at power management capabilities in the next generation hardware and even the existing hardware which we have, be it on the compute side, be it on the memory side. Telemetry and also the workload profiling is another space which we look at. So we're looking at our workload profile, which workloads are basically more resilient. Some workloads require 3 nines, some workloads require 5 nines. And the last thing is the data center telemetry. And we're basically integrating all of that together in a software layer to make sure we are delivering the best possible solution and reduce the gap. The gap when you say the actual versus the provision, how do you go and make that gap smaller so that we can go and leave no power behind as we go look at our future data centers as well as the solutions. What's next? We know we are not going to be able to solve everything in our current infrastructure. We are looking ahead. We are looking ahead from a silicon perspective. We are looking ahead from a systems perspective. And we're also looking ahead from a data centers perspective. Today, we are looking at the cold plates. What's next? We are looking at microfluidics. Essentially, instead of having a cold plate, how do we go and basically cool it at the IC level or a silicon level? We talked about the pods. We are seeing that copper has its limitations. When you're basically putting 72 or more GPUs over there, you're still connecting them through a certain copper fabric. You heard that data center to data center is moving to optics over here, but that needs to move back into even the rack, inside the rack, and rack to rack. Because there is a lot of opportunity to go remove the lossiness which comes with copper. At the same time, remove a lot of the retimers which come with that at the rack level. So we are looking at opportunities and how to get more optical networks into our system design, be it within the rack or rack to rack. And the last one is, which today, for those of you who were at the Satya's keynote, also saw the timber data centers. As we look at it, they are much more efficient from a carbon footprint perspective, better for sustainability, and most of all, they are also basically more efficient from a power perspective. So we're looking at all opportunities. We will continue to work with our customers. We will continue to work with our development partners to look for even more opportunities over there. So Saurabh talked about a lot of the chips and all of the different things. We have them over here. We are going to bring them in the front after the Q&A session. So if you want to go and see and feel them, you can go and look at them at that point. Thank you, everyone. It's great to see you all. We will open it up to question and answers. I'll ask Saurabh to join me. Please feel free to come to one of the mics if you have a question.
A lot of the goodies here. We've got the DPU, Maia, Cobalt, so feel free to stop by and have a chat, but happy to answer any questions. Yeah, we covered a lot in 40 minutes, so anything in the room, and I know there are probably some online questions as well, so I'll look at Carlos and Pat if there's anything we could answer from there. Awesome.
I have a question. What's the timeline for the new HSM solution being offered?
So the new HSM solution is being integrated into our next generation servers. So sometime next year, we haven't decided to give the timeline yet. But it's in our labs, it's being validated, and the software stack is being brought up. So clearly in the very near future. Yeah.
You mentioned that the last slide there, that the new data center is more power efficient.
That's right.
How so? I mean, from the carbon perspective, I get that, but how would they be more power efficient?
So basically, the Timberwood power centers. So essentially, there's two things over there, right? Basically, the lossiness from a perspective of how the airflows is designed over there in these data centers, they're being looked at grounds up from that perspective. Saurabh,
We also, at least from an infrastructure perspective, we are also making sure that the new designs are natively liquid cooled. That gives you a higher PUE than like air-cooled data centers. We're also looking at like how do we place these inside the data centers? So what kind of PDU structures we do and things like that. Gohar covered some power management techniques that are optimizing workload profiles as well as being able to take telemetry out of the data centers. So the next generation of data centers, if you combine the construction, if you combine the placement and the availability, like how do you make sure we design it for liquid cool? If you combine some of the advanced telemetry that you can take from these servers so that there's an opportunity that you can go and optimize it to the fully provisioned power. You take all of those steps in, the PUE definitely is clearly a big improvement over our previous generation data centers.
just to add to that, right, even if you look at today's the heat exchangers and stuff, if you have a centralized heat exchanger as we go into the new data centers, which are efficient, you can go and eliminate more power dissipation when it comes to that.
It's not just the wood.
It's not just the wood. It's basically the next generation design.
Yeah.
No, good question.
Can you talk about the hollow core fiber at all?
I have limited experience in that piece, so I'll just kind of brush up on top of it. But right now, it's mostly the hollow core fiber technology is being used for long fiber haul things, and it's really about making sure that we can meet the demands of the network infrastructure. I showed how much fiber is being produced, so that really helps us consolidate it as well. But yeah, happy to refer you to some experts there.
Are they
A little outside my domain. Yeah. Perfect.
We'll do that. Go ahead.
Sorry about that.
This is Mark. General question. Do you know when the Denmark East region is going available?
When is the Denmark East region going live?
I don't know
I'll
what
have
the
to.
exact answer for when the region can go live, but if you want to hang out afterwards, I can probably point you to some
We
content.
can maybe offline talk and give you more information. Go ahead.
As power demand starts to grow and everything, you guys work alongside before the power gets to the data center to power providers to see if there's any more efficient way to provide power to you guys or more efficient anyway?
Yeah. You want to take that?
Yes, I can do that. So our data center design teams, our data center operations teams are working much ahead in planning of what hardware will go there. They're working with the utility companies and everything to go and make sure that they're optimizing it as we look at from a footprint perspective, as we look at from the green energy perspective. Yes, Microsoft is actively working on how to get the green energy over here. And yes, that's a key part of the data center deployments.
Yeah, just to add on that, obviously carbon-free energy is one of them. We're also, next generation data centers, we're also looking at what kind of workload profiles run in, and we kind of provide that feedback back to the utility to make sure that we have the, when we move into a region, we don't, cause interruptions and everything to the other data center. So it's a very closely working relationship there. We study all of our workload patterns. We do have inbuilt infrastructure in the data center as well, whether we add UPSs, whether we make sure we add some filtering equipment to make sure that the resonance doesn't feed back into the grid. So it is definitely a close partnership with the local utility provider.
I have a question along those lines. Like, how is Azure looking to avoid an issue like they had with West Europe, where the government made decisions despite their best plans to basically halt all growth, not just for Azure, but all cloud partners? Obviously, efficiency and growth is important, but working with the governments is also equally important. And that's put pressure on customers who are relying on West Europe as their region.
Yeah, so just paraphrasing your question, how does Azure work with government agencies to make sure that as we are trying to grow up certain presence or footprint in our government agencies, we are working with the government to understand, the regulations around it, what the growth is, and what does it do to the kind of the utility and everything. I think it's a great question. I don't think there's a one clear answer because every government agency is different. But one of the things that we are doing is definitely working closely to make sure that we are securing more carbon-free energy resources. We are making sure that we are coming in with the right demand profiles into this thing and making sure that we are having those conversations early on. So we have a full, under Brad Smith, which is our kind of a legal team, we have a full team that works on this and make sure that when we do enter a certain region, we are making sure we are working with the government there to get things. So yeah, great question, and I'm sure there'll be a better answer from our government affairs and legal team.
Hey, again, we're at time. Thank you. Thank you for the interest. If you have any questions after that, feel free to stop by.
Thank you. Thanks for taking the time.